Okay, so in our previous videos, we have talked about simple linear regression, how to fit the simple linear regression model, and what are the assumptions we need in order for the model to be valid. Now let's see how we could use the simple linear regression model that we have fit. Now suppose your fitted line is like this, y hat equals to beta 0 hat plus beta 1 hat times x. In order to use this fitted line to predict any response value y for a given number of x, it's kind of like pretty straightforward, right? You just plug in your x, whatever x is given to you into this model and you compute the new y value. There is a thing that you need to be careful. That's called extrapolation. What does that mean? That means you are predicting the values outside the range of your data. So this is predicting values outside the range of your data. This is generally a bad idea because you don't know what your pattern looks like outside the range of your data. So this is generally a bad idea since you don't know if the observed trend continues. For example, here we are trying to predict the age of first marriage of Americans. Now, we collect data from, I think it's from 1890s to 1930s. And this is the age of women on their first marriage. And you could see, okay, it seems like it's decreasing, right? The age that women first get married is decreasing. Now, this is the trend of the data that we've been observed based on the value we collected. Now, if we want to predict, okay, what do you think the average age women first get married at year 2020? I'm sorry, 2000. Now, if you are trying to predict the y value using an x outside the range, then you may think, okay, the pattern of the data may be like this, right? Oh, it seems like maybe by at year 2000, the average age maybe 21.5. That is so wrong because the pattern you have seen are just for the data points in between 1890 to 1920 or 1930. You can't use a x value outside the range of your data to predict the y because you don't know whether the trend still continues. To be honest, you may not be surprised to see actually the true trend is like this. Around 1950 or 1960, the average age of marriage actually starts to go up. Now you can definitely see that outside the range of your x values, you don't know what the trend would be like. So this is not a good. You can't estimate your y using the x value that's outside the range. This is a typical extrapolation problem. So having said that, let's take a look at the following example using the pH value example that we have seen at the beginning of this handout. I hope you guys still remember our motivating example here. We are trying to study the relationship between the pH value of the water and the percentage of arsenic it removed. So we try to use the pH value to predict or estimate the percentage of arsenic being removed. So for this example, first find a fitted least square regression line for this. And are the simple linear regression assumptions met? Now let's go to the StatCrunch to take a look at it. And in your homework, you are asked to do a question like this as well. Because we are going to have an open book final exam, it's not going to be surprised if you are going to see a question like this as well. You should know how to use technology, for example, StatCrunch, to perform a simple linear regression and read the results from the output. Okay, let's take a look at the StatCrunch. So here is the StatCrunch, and the data is here. It's posted on Moodle called pH. I just copy and paste the two columns here. So we are trying to fit a regression line. We go stat regression. We are fitting a simple linear regression model. Simple linear regression model. So we are using the pH to predict the arsenic being removed. So the x variable, which is our explanatory variable, should be the pH value, and that's our variable 2 here. The y variable, which is the arsenic being removed, that's our response variable, is going to be this removed, that is VR1 here. I'm going to leave this out here, and let's include all the graphs here. We actually don't need that much, but let me include all of them here. We can see what they are they could provide you. So go compute. So here, this is your result. You have the regression line. You have the sample size, the correlation coefficient R. We have talked about it, and we actually used StatCrunch to calculate the R before. It's negative 0.95. It's in our page 4 of our handout. That's the same as what we have got. And this R squared, we will talk more about it later on. Now here is our parameter estimate. This is the intercept estimate is 190.26. The slope estimate is negative 18.03. This is a ANOVA table. We didn't talk about ANOVA, so let's ignore it here. We also didn't talk about the inference for the regression, so we are not going to talk about this part as well. But if you learn more stats in your future class, you could see that those p-values are significant, so those intercept and slope estimates are significant. But right now, for this course, you just need to know, okay, for this model, the intercept is 190, the slope is negative 18. So the fitted regression line would be y hat equals to 190 minus 18x. Now let's take a look at the assumptions. let me switch it to our note, and let me write it here so that we could do it. It may be a little bit slow this way, but I feel this may be better. So the fitted least square regression line would be by height equals 190 minus 18x. This is the fitted regression line. Now let's take a look at the SLR assumptions. You guys still remember what are the 5 assumptions we have talked about? First, if it's linear. Second, are the samples independent? Third, are the residues normal? Fourth, are the residues have equivariance? And the fifth is whether it's average to 0 or not. Now let's take a look at the graph that's being provided by StatCrunch to see whether those 5 assumptions are met. So let's go back here. This is the scatter plot. That VAR is pH, VR2 is pH, VR1 is removed. So let's ignore those green and yellow line. We didn't talk about that. Just take a look at those dots and this right line. It seems like, yeah, it's a reasonable linear relationship between your x and y, right? So for the linear assumption, yes, this is observed by the scatter plot. And independent, and this assumption is also yes, right? Because when you go back to read the question, it's reasonable to believe that she's collecting independent samples. So if the samples are independent, then the observations are independent, your y values are independent. So this is yes, samples are independent. The third assumption, normality, whether the residues are normal. So this should be checked by the QQ plot, right? So let's go back to StatCrunch output. Here is the QQ plot. The x-axis is the normal quantiles. The y-axis is the observed residual quantiles. You could see it's kind okay. It's kind of okay, right? Your QQ plot, all those dots are pretty much close to this right line, right? If that is the case, then this is a normal distribution. If, say, your dots look like this, then that's not a normal distribution. So the normal assumption also satisfies. So yes, this is tracked by the QQ plot. The last two assumptions, the constant variance and the average to 0 residues could be checked by the residue plot. So let's go back to StatCrunch. This is the residue plot. We are interested in the residues versus the predicted values. And you can see here is the 0, right? And the values are pretty much scattered around 0 with no obvious pattern. So the average to zero assumption is met, the equivariance assumption also met because there is no obvious pattern. You can the predicted value versus residues is the most used residual plot, but those are also used as well. Sometimes you can see this is the residue versus the VR1. This is the VR1 versus the residues. They all could, this is the residue itself. This is the residue versus the index. You could see they all could show you there is no obvious pattern of the residues. The residues are randomly scattered around zero and with constant variance. So we could go back to the node, and so this is yes, this is also yes. Those two are by the residue plot. You don't have to use StatCrunch. You can use whatever technology that you feel comfortable. It's just I'm showing you the StatCrunch as it's free to NC State students. If you have other softwares or technology that you're more comfortable with, you're welcome to do it, and you're also going to get credit as well. So the second question, interpret beta hat, beta zero hat. So beta zero hat is the intercept, right? That's 190 based on the output of StatCrunch. That means if your pH value is 0, then you would expect 190% of arsenic to be removed. This is how you should interpret it. And is this interpretation meaningful? Actually, no, right? Because if you take a look at the data, let's take a look at our data from StatCrunch again. The value for your pH ranges from 7.01 to 9.87, right? If you take a look at the scatter plot, it's this pH value equals to 0 is outside the range of X that you collected from the sample. And we have talked about it. If you are using a X value that is outside the range of the data you collected to estimate Y, that is very dangerous. You shouldn't do that because that may not be the trend or the pattern of the data outside the range of X, and that is called extrapolation, right? So it is not meaningful. The interpretation of this beta zero hat is not meaningful. So we just use this estimate to help us to predict Y when we have X within the range of the data. So it's just a number that's helping us to predict. This number itself is not meaningful because pH equals to 0 is not within the range of X. Now, the interpretation of beta 1 hat, that's -18. That means for 1 unit of increase in the X value, the Y value that can be removed is expected to decrease by 18% on average. So this one should be on average too, because they are talking about the mean of the y. So that's question number 3. Question number 4. If I got a sample with pH equals 8.2, what is our predicted y should be? So our predicted model is 190 minus 18x. Now we plug in this x equals 8.2, we will have 190 minus 18 times 8.2, that is 42.4%. Please note here, this is meaningful because this x equals 8.2 is within the range of our data. So this is the predicted value of y. After going through this process, the engineer actually removed 37% of the arsenic. Now the residue would be the actual value being observed minus the fitted value or the predicted value. So when x equals to 8.2, the actual arsenic being removed is 37% minus the predicted value that we have just calculated in part 4. This is negative 5.4%. And please note that this residue is observed minus the predicted. The sign does matter, so don't switch the order of this yi and yi hat. Last question. If another sample with pH equals to 6.2 is provided, can we use our regression line to predict the percent of arsenic that can be removed? Remember, we have mentioned that the range of the pH that's being provided to us is from 7 to 9.8 something. And the 6.2 is outside the range of the data. So no, we can't do that. The 6.2 is a pH value that's outside the data range. So we can't do it. This is an extrapolation problem, right? And we have talked about it's this. This is generally a bad idea. You shouldn't do it. Okay.